Hi everyone, let's start another coding session of Keras code examples. So today's code example we'll be dealing with image classification via fine tuning with EfficientNet, and if that's the code example we need to understand that the model architecture is not the concern, but the concern is what exactly is fine tuning. So fine tuning is the case whenever you have a pre-trained model network with you, and the weights of which are provided to you. So you don't want to train the model from scratch. Let's say uh, you don't want to define the model architecture and define and start training from the scratch. Rather, if someone has already trained on something and has shared it publicly on the internet that this is my pre-trained weights, you can find on pre-trained weights at multiple places. Keras, Keras provides pre-trained weights, Google TensorFlow provides pre-trained weights, PyTorch provides pre-trained weights, ONNX provides pre-trained weights, uh, OpenAI, many companies provide pre-trained weights. Hugging Face Transformers provide pre-trained weights. So what exactly is the idea of pre-trained weights? So you have pre-trained weights. You don't want to start the training from the scratch. Rather use the pre-trained weights and tweak it a little bit so that you can understand, so that your training can be done faster and with a higher accuracy compared to the one had you done it from the scratch. So for this example, we'll be using EfficientNet. So EfficientNet is primarily in two versions. So EfficientNet, there are two versions, B1 and B2. That's not important. So B1 we have B0 to B7, and the B0 signifying the smallest one of them all, and B7 is the largest one of them all. So the one which is the smallest one of them all has the least amount of parameters compared to the B7, which is the largest, has the maximum amount of parameters. So B0 to B3 are kind of ideal and suitable for mobile and edge devices compared to B4 and B7, which are only good if you are implementing on a high-end GPU server, or you're very much concerned with accuracy, let's say in medical cases or medical diagnosis. So in those cases, let's say you upload an image and you want the accurate prediction, then in those cases you want to have this B0. You have every variant has an image resolution, different image resolution, which is provided here. So the one which we are dealing with, just before using a pre-trained model network which is already defined by TensorFlow class applications, just check the image resolution, default image resolution. So there are two way outs. Either you can tweak the input image to this particular resolution, or you can change this particular image resolution and the entire architecture, but that is kind of tedious to do. So there are two methods. Either, just a sec. So regarding input image, there are two methods. One is the model resolution. So check model resolution, and after that you resize the dataset images to that. Whereas opposite to this would be tweaking with the model input config. And how do you do that? To do that, or to achieve that, what you do is there's a parameter known as input size in the conf2d, or the first layer of the model. You tweak with that, but this is complex. We'll discuss this at a later stage, not at this point of time. So you have your model with you. And since you have your model with you, what you can do is this is how we implement the model. So you have this particular parameter, weights. Weights can be none, it can be ImageNet, or it can be a particular weights file. Let's say the file name is abc.h5, either of these. So here we are using the ImageNet weights, and include top equal to false means you are removing the last layer. So if you don't have top equal to false, let's say you have include top equal to true, you obtain the model summary. You'll observe that the last layer has dense layer, which is predictions and 1000 node. But if if you remove that, that would be removed. Isn't it quite obvious? If you remove that, basically the dense layer won't be there anymore. Instead, it would have some average pooling or those kind of layers in the end. So now we have the end layer as top, batch normalization and activation. On top of it, we can add some layers. So that is the idea of fine tuning. So fine tuning, so basically fine tuning, in the fine tuning thing you have this is the entire model. In the model you have end last layers after the convolutions are done. This is still here, we have convolution layers. After convolution layer we have the classification head, or which is known as the dense layers. So you remove the dense layers and then on top of it add a new dense layer to it. This is one method. Or in addition to that, there are methods which we can discuss here. As you can see in this particular code example, what they are doing is they are taking Stanford state-in-the-art data set. So image size is 224, this and this is basically how you initiate a TPU. So this is quite standard. If you want to initiate a TPU, this is a piece of code you need to have. And but what concerns us the most is the resizing of the training data set. So in this particular code block, you can see size equal to image size, image size. What does this mean? So basically, the dataset was loaded here, but the dataset might have a different dimension. So what you want to do is that change the training dataset dimension to what you require or what the model input resolution matches, so that there's compatibility. Here you can see they have visualized the image. So what is more interesting is the data augmentation. What is data augmentation? Basically, you have image samples. This is one image sample. This is one image sample, but the entire dataset contains only 1000 images, and you feel that is not sufficient to train a model or to reach the optimum results. So what you do is have data augmentation in the case when you have data scarcity and cannot obtain additional data in the near future. So what you do is you obtain artificial data using statistical methods, and such a statistical method is known as a data augmentation. So data augmentation has two types. One is statistical method, another is deep learning methods. The statistical method can have random zooming, shearing, flips, and many other several methods. But the deep learning method is when you want you don't want duplicacy in it. So this particular adds in a kind of duplicacy. So there was this image A, Z. So if you do a flip, it would be like this. If you do a zooming, it would be like the entire Z would be zoomed out and a part of it would remain. Maybe something like this. It is zooming. Maybe shearing can be done. So basically you have original image and you're statistically transforming that to obtain new images. So there is a high similarity match between these three images, and kind might lead to overfitting. So this is done. This is much faster and easy, quick helps you in quick prototyping, whereas this one is a research-based kind of project. It would take you around some time. Is implemented using GANs. Let's say you have 10,000 dog images. You will train a program or those kind of network, and based on that, program would generate another as many as samples as you want, based on the learning which it had obtained from these 10,000 images, and based on that learning, it would generate another image which will be seemingly realistic but very hard to identify and will not be any one of these. So this is what deep learning method is. This gives very better high fidelity results, but it's not easy to implement and takes time. So this is the difference, and these are the two types of data augmentations which are readily available, which are quite more popularly used. So once you've done that, you can see this is a statistical method, and you can see it's just being rotated around, and from one image you can have 7 to 8 different new images. Now we discussed that they are preparing the input. So what is the pipeline? What is the flow of the code? Flow of the code is nothing but get the image size set, have your model decided before starting the coding. whether we want to train on GPU, CPU, TPU. Since they're wanting to train it on TPU, you have the TPU instance defined. If you want to train it on GPU, you need not to have this code on. Just turn and plug on the GPU code. Then have your dataset loaded. Once the dataset is loaded, as per your decided model and the model's resolution, resize the dataset size. Once that is done, you can quickly visualize the dataset. If you realize that the number of samples in the dataset is low, then you can have a quick data augmentation. The types of data augmentation are dependent on the dataset. Don't randomly apply data augmentation. Let's say you are doing check verification, so you don't want to randomly flip the check and add it to the data sample, because that would be erroneous. So depending upon the context and the use case, you perform the correct set of data augmentations. Once that is done, you prepare the inputs. For preparing the inputs, we have, so till here we are still preparing our data. We loaded the data, we resized the data, then we quickly visualized the data. We realized the data does not have as many samples as we require. We augmented data. Now we are done with the data. Now we need to make the data ready to be sent to the model. So model cannot readily accept all kind of data. So we need to process the y variable. So we have x is the image is the x variable, label is the y variable. So we have TF one hot encoding. What is one hot encoding? This is one hot encoding. So let's see your classes as apple, banana, lemon, tea, and this is apple, banana, lemon, tea. So let's say for t, how it would be represented as 0001, and rest also 0. So this is one hot encoding. What if you have 1000 samples, 1000 different possibilities? Then one hot encoding is quite memory intensive, and we switch to sparse cross entropy. So this is one thing. Now the dataset y variable is configured. Once the y variable is configured, you want to convert the dataset into batches, and for that you require dstrain.batch, and from that you do drop remainder equal to true. What does this particular mean? Let's say you have 640 samples in one dataset. If the batch size is set to 32, you will have 0 remainder, but the number of image samples is 640, you will have 10 remainder, and you don't want to add those 10 remainder because it might lead to faulty results. So it's better to drop the results, drop the remainder. So that's a standard practice. Now the dataset is completely configured. You move on to training a model from the scratch. This is just for illustrative purposes. We are not going to train the model from the scratch. The idea is to learn fine-tuning. It just shows that after training a model from scratch without any pre-trained weight, as signified from here, that the weights are none. So you can see that the model accuracy for validation and training are quite low. Training is 60% and validation is even much lower, is 20-22%. Whereas if you were to use a pre-trained network like EfficientNet, then the model accuracy would be much higher. So this is what we are doing, is we are taking in the inputs, defining this would be the input, adding the augmentations. Then to the model, we are defining that the input tensor would be x. And what does this mean? Model trainable equal to false. This means that this is your entire model. This is the classification head. This part of the model is being set to trainable equal to false. What does this mean? This means that whatever is the pre-trained weights, don't touch it. Whatever is the newly added code, which is these particular lines of code, the top layer, global average pooling, batch normalization, dropout, this is added on top of, and the dense layer for the classification as per the number of classes. These 4 layers are added to top of the model which was already present. So these are the ones which will be trained, and rest of the model won't be trained. And the training will be done with the help of optimizer, atom optimizer, learning rate, whatever it is. So this part, if you set it as freezing equal to true, then this will not be trained. This will only be trained. Also, there are some people, and as you can see, this method drastically increases the accuracy. The training validation accuracy, which was earlier as 22%, is now at 76%. And training onboard training accuracy remains the same. But sometimes it is beneficial to train. So how to freeze and unfreeze is dependent upon chart, which we may discuss at a later stage. If the dataset is large, if the dataset is small, if the dataset is similar to if the pre-trained weights, the model weights, which are the pre-trained model weights, that it must have been trained on a certain dataset. If that dataset is quite similar to your dataset, then there's a different approach. If it is quite different, then train from scratch. If it is similar, then what to do, then what not to do. We can discuss it at a later stage. So every model has three different parts. One is the low level features, other is the mid level feature, and the last is the classification part. In fine tuning we usually deal with classification, and this part is always trained, but sometimes a part of middle level features is also picked up and trained. But what does low level and mid level feature signifies? So a low level feature would construct features like line, curves, this kind of curve, this kind of curve, maybe this kind of curve. This is low level features. Low level. These are low level features. Whereas many low level features are combined together to make mid level features, and many mid level features combined together to finally obtain the result. So we might want to take out part of it. Like, we are not dealing with human faces, we are dealing with animals. So although the low level features would remain the same, we might want to take a part of the model which is in the mid level features and train it back. So that's what they are doing. They are taking the last 20 layers, making it trainable as true. And what does this line mean? If not instances, batch normalization. So batch normalization is not usually trained in fine tuning. Just remember this. It's quite important. If the instance is not batch normalization, never ever make the batch normalization layer trainable while fine tuning, because that might actually mess up the model training. While fine tuning, never ever make the batch normalization layer trainable, as well as while testing, batch normalization should not be trainable. So you can see there's a lot of jump in the training accuracy, although the validation accuracy remains stable, but remains the same or slightly increases, but is quite stable. So what are the tips on fine tuning? So let's summarize what we learned. We have learned that fine tuning is nothing but the removal of the classification head, which is done by include top equal to false, then adding layers on top of the model which we have at hand or which we have decided to proceed with. This can be done by defining the layers and adding on top of the model. Fine tuning is basically what part of the model has to be trained. If you are training with entire scratch, that is not fine tuning. If you are training the classification model, you can train the classification head. That is fine tuning, a little beyond classification head and a lot beyond classification head. Let's monitor upon the last 2 points. A little beyond classification head is the case when you realize that the dataset on the pretrained weights on which the dataset on which the pretrained weights have been obtained is quite similar to the dataset at hand on which the task is provided to you. You can just take the last few layers of the middle features, whereas if it's slightly more different, then you can take more layers. So that is what it is. But basically fine tuning is the art of using and how much to train and how to train the pre-trained models. So that is what it is. Input image. Now I think we discussed this. Alright, so that is what it is. This is what the session is all about. I hope you understood and had a wonderful time. In case there's any query, just feel free to hit out in the comment section. In addition to that, I'll provide a link to this particular Jamboard. You can access that in the description box. Alright, have a great day ahead. Bye bye, take care.